The fundamental nature of magnetism is to be found in interactions involving electric charges in motion. A magnetic field is established by a permanent magnet, by an electric current in a conductor, or by moving charges. This magnetic field in turn exerts forces on moving charges and current carrying conductors. We now will begin to study these magnetic forces and examine the ways in which magnetic fields are produced by moving charges. A compass needle only points north because the Earth's geographic North Pole is in fact a magnetic South Pole. This sketch of the Earth's magnetic field have lines that show the direction a compass would point at each location. These lines are actually magnetic field lines. The direction of the field at any point can be defined as the direction of the force the field would exert on a magnetic North Pole. Later we will introduce a more fundamental way to define magnetic field. In 1819, the Danish scientist Hans Christian Ørsted discovered that a compass needle was deflected by a current carrying wire. A few years later, Michael Faraday in England and Joseph Henry in the United States discovered that moving a magnet near a conducting loop can cause a current in the loop, and that a changing current in one conducting loop can cause a current in another separate loop. These observations were the first evidence of the relationship of magnetism to moving charges. In describing the interaction between two charges at rest, we introduced the concept of electric field, and we described the interaction in two stages. So we have one charge sets up an electric field E in the space surrounding it, and two, the electric field E exerts a force F equals QE on a charge Q placed in the field. We will follow the same pattern in describing the interaction of charges in motion. So here, 1, a moving charge or current sets up a magnetic field surrounding it, and then 2, the magnetic field exerts a force on a moving charge or a current in the field. Like electric field, magnetic field is a vector field. That is a vector quantity associated with each point in space. We use the symbol B for magnetic field. Here we will consider the second aspect of the interaction. Given the presence of a magnetic field, what force does it exert on moving charge or a current? Later we will return to the problem of how magnetic fields are created by moving charges or currents. So the magnitude of a magnetic force upon a 2 microcoulomb charge will be twice that upon a 1 microcoulomb charge at the same velocity. The force is also proportional to the magnitude or strength of magnetic field. The same charge moving through a magnetic field twice as strong will experience 2 times the force. The magnetic force also depends on the particle's motions. This is quite different from the electric field force, which is the same whether the charge is moving or not. The magnetic force is found to have a magnitude that is directly proportional to the particle's speed. A particle at rest experiences no magnetic force at all. The direction of the force is determined by the directions of the magnetic field B and the velocity v. In a very interesting way, the force F does not have the same direction as B, but instead is always perpendicular to both B and the velocity v. The magnitude force F of the force is found to be proportional to the component of the velocity v perpendicular to the field. When v and b are parallel or antiparallel, there is no force. These characteristics of the magnitude force can be summarized with reference to figure 1 as follows. The direction of force vector F is perpendicular to the plane containing the vector v and the vector field, magnetic field B. Its magnitude is given by F equals Q, the charge, times the perpendicular velocity times the vector magnetic field B, which equals Q times the velocity v times the magnetic field B times sine theta. So q is the charge and theta is the angle between this velocity vector and b, the magnetic field vector. This description does not specify the direction of the force vector F completely. There are always two directions perpendicular to the plane of the velocity vector v and the magnetic field B, but opposite to each other. To complete the description, we use the same right-hand thread rule used to define the vector product. Imagine turning the vector v into the magnetic field vector B through the smaller of the two possible angles. The direction of the force vector F is the direction in which a right-hand threaded screw would advance if turned the same way. Alternatively, wrap the fingers of your right hand around the line perpendicular to the plane of V and B so that they curl around with this sense of rotation from V to B. Your thumb then points in the direction of F. So if we curl our fingers around, V is going in, so we can see V going towards B there. So if we put our fingers as if we're curling around, then the direction our thumb points is the direction of the resultant force vector. So in this case it's up out of the page, so we've drawn it here as F. So we're going from V to B and thumb is pointing in the direction of the force vector F. Thus the force on a charge Q moving with velocity V in a magnetic field vector B is given both in magnitude and direction by the vector field F equals Q times the vector V, velocity vector V, crossed with the magnetic field vector B. So we've written that here. And you know that this is a standard cross product, so if the magnitude of that is simply the cross product, magnitude of F equals the magnitude of this V times the magnitude of the magnetic field B and sine theta, which is the angle between them. Yeah. So this is a nice shorthand way of encapsulating all of this information. You can tell here, like for example, if theta here is 90 degrees, then we end up with F equals QVB, and that's going to be the maximum force when V is completely perpendicular to B. You can tell that by plugging in 90 into this angle phi. You'll get sine 90 is 1, so you get F equals QVB. So the force will be at its strongest when the velocity of the charge is completely perpendicular to the magnetic field that it travels through. This is the first of several applications of the vector product we will encounter in our study of magnetic field relations. Finally, we'll just note that we may interpret B sine theta, we may interpret that as the component of B perpendicular to V. That is B, the perpendicular component of B, giving F equals Q V B perpendicular. So that's another way of writing it, although equivalent to this equation here. This form is sometimes more convenient, especially in problems involving currents rather than individual particles. We discuss forces on currents in conductors later on. So in this diagram here, if you want to use this form, all you just do is mentally just swap over magnetic field vector B and the velocity vector V. If you just swap that to B and that to V, then everything will come out the same using this equation. It's just another way. We can look at it in terms of the velocity V or look at it in terms of the magnetic field vector B. Either way is equivalent. Sometimes it's easier in calculation to use this version.